Okay, hey guys, it's Miss Adelini. Our last video is about resting potential in nerve cells when they're not sending signals. And this video is going to be about the action potential in nerve cells, which is when they are sending signals down their long axons. So on this page, where we see an image of a voltmeter measuring the resting potential of a nerve cell, you're going to draw a little key to show yourself some of the molecules that are involved in sending an action potential. So you're going to draw the sodium-potassium pump, which, if you'll recall from our discussion of resting potential, is used to pump 3 Na plus out of the cell while pumping 2 K plus into the cell. You're also going to show a voltage-gated sodium channel. By voltage-gated, I mean that it's normally closed and it only opens when there's a change in charge in the nerve cell. We're also going to draw a voltage-gated potassium channel. Note that it's slightly different. I have these two rectangles on the sides instead of these little ovals. And again, it's normally closed except if there's a change in charge in the nerve cell. Okay. So we have several stages of an action potential. We've got the stage name on the left, the description in the middle, and an image on the right. So the first part is threshold. Threshold is when we have some stimulus. Note that I'm showing the stimulus acting upon this nerve cell axon. So above the axon is outside the cell, and below the axon is also outside of the cell. So we're showing a stimulus, and it is causing positive charge to enter the cell. Remember, our normal resting potential is -70, so if we have positive charge entering, it is getting closer to 0. If it reaches -55 millivolts, we've reached threshold, and we're going to start the action potential. At this point, we do have our sodium-potassium pump working just like it normally does, but our voltage-gated sodium and potassium channels are closed, so I show the gates being closed here. If we reach -55 millivolts, or the threshold level, enough positive charge has entered the cell that we can start the next stage, depolarization. So in my next picture, I'm showing positive charge causing the voltage-gated sodium channel to open. Since we normally have more Na plus outside of the cell than inside, the sodium is going to move from a high concentration outside towards a low concentration inside. And that is going to further raise the potential of the nerve cell. So again, we're going to be moving from -55 towards 0, and that's called depolarization. Now, the voltage-gated potassium channels will also open in response to this positive charge. However, they will be slower. So, during our next phase, which is called repolarization, we're going to see our voltage-gated potassium channels opening in response to positive charge. However, because we normally have higher K plus inside the cell, the K plus is going to leave. Having this K plus leaving the cell is going to cause the inside of the cell to become negative relative to the outside. So we are repolarizing our cell. The K plus channels take a really long time to close, so they do let out some extra K plus. That's called the hyperpolarization or undershoot phase, and they cause that membrane potential to dip below its resting state. So below -70, even down to about -80, as those K plus channels are struggling to close. So we're going to have about the same picture in hyperpolarization. It's just more K plus leaving. Okay, now we're going to come back to the resting phase. We're going to end the sending of the signal when both the Na plus and K plus channels are closed, and we're going to be pumping Na plus back out, and we're going to pump K plus back in, and eventually that'll get us back to -70 millivolts again. Okay, now these two graphs are going to show us how the voltage on the inside of the cell changes at the different stages of the action potential. So we started out at -70 at resting. we have some sort of stimulus that brings positive charge in and gets us to negative 55, which is our threshold value. Then our Na plus channels, our voltage gated Na plus channels, are going to open, and Na plus is going to rush into the cell, causing this depolarization and increase in charge inside the cell. Once we hit the peak of the graph right here, our Na plus channels are going to close, so no Na plus is going to be entering the cell, and our K plus channels are going to open. K plus will exit the cell, bringing the cell's voltage back down again, and since our K plus channels are so slow to close, we're going to dip under the resting membrane potential. That's called undershoot or hyperpolarization, until our sodium-potassium pump is able to bring us back to negative 70. This is what that's going to look like traveling down an axon. Okay. So if our action potential starts here along the axon, and we have Na plus channels opening to allow Na plus to come in, which is the depolarization part of the action potential, the rest of this axon has not yet been exposed to the positive charge, so it hasn't opened its Na plus channel, so it's still at resting potential, negative 70 millivolts. Now, once our positive charge comes in, it's going to cause more Na plus channels along here to open, and we're going to see the action potential moving farther and farther down. Right behind it, we see the potassium channels opening, and we're going to see hyperpolarization and repolarization. So we're going to see the action potential sweeping down, and eventually the beginning of that axon is going to return to resting potential due to the sodium-potassium pump. Okay. And that's it for now on the action potential.